Okay, so now we're going to take a look at some of the trends in the reactivity of some of the elements on the periodic table, and we're just going to focus on the main group elements. Okay, so we're not going to be looking necessarily at the transition metals, the D block or the F block. There's a whole chapter in your book that talks about transition metal chemistry. We're going to save that till the end. If we have time, we'll talk about that at the end of Gen Chem 2, for example. If there is time, we'll discuss it then. Otherwise, we're going to focus on the main group elements. And again, the main group elements, these are in groups 1A through 8A, right? So the 2 columns on the left side of the table and the 6 columns on the right side of the periodic table. And those are the same groups that we looked at when we looked at general periodic property trends, things like atomic radius, ionization energy, electron affinity, electronegativity, all that stuff. It was the same main group element or representative elements that we were looking at. All right, so main group elements are also called representative elements. That's another term. And what's going to be key to our understanding of the reactivity now, so this concerns the chemical reactions that they undergo, are 2 properties. The ionization energies, so that's the IE, and the electron affinity, which is their EA, right? So as a quick reminder, the ionization energy, okay, this is a measure of the amount of energy needed or required to remove an electron from an atom in the gas phase. Okay, so how easily, in other words, how easy is it to remove an electron? If the ionization energy is high, that means it's not very easy. If the ionization energy is low, it's very easy to remove an electron. Electron affinity, on the other hand, is the ability of an element to attract electrons to itself. Okay, and the interplay between these 2 things will help explain some of the reactions, the reactivity that we will observe. So for example, sodium chloride, table salt, right, is an ionic compound. It's formed from elemental sodium and elemental chlorine. Why do they react this way? Well, sodium has a very low ionization energy. Okay, so it can easily lose its first electron. So it's got a low first ionization energy. So it prefers to be then lose that electron from the Na plus. And on the other hand, right, the chlorine has a energetically favorable electron affinity. So it has the ability to attract electrons from another source, right? So the chlorine here can or wants to attract electrons from something else. So they can help each other out, right? The sodium loses its electron very easily. The chlorine wants the electron. It forms a negative ion. And as a result, these 2 things come together to make our ionic compound, where we have positives and negatives right around each other. Right, so we can use the IE and the EA, ionization energy, electron affinity, to try to explain some of the reactivities that we're going to observe. So the first thing that we have already broached or we've alluded to earlier in the semester is the fact that elements that belong to the same group usually have similar characteristics. So they behave similar to each other in a chemical sense. Okay, and that's generally the case. However, there are some exceptions. And usually what we find is the first element in each group behaves a little anomalously. And that can be attributed to that first element in each group being incredibly small relative to everything else in that group below it. All right, so generally, yes, elements in the same group will have similar characteristics, chemical reactivities. However, the first one is slightly different because of its much smaller size compared to everything else in that group. Okay, so another trend in reactivity in some of the main group elements is known as a diagonal relationship. And what this is a similarity in some of the chemical reactivity between pairs of elements that actually belong to different groups and different periods. And they happen in a diagonal type relationship, right? So for example, lithium behaves similar to magnesium, even though they're not in the same group, but they're diagonally next to each other. Beryllium and aluminum behave similar to each other. They're diagonally next to each other. And then boron and silicon behave similar to each other as well. All right. So a good example of this would be the reaction of lithium with nitrogen to form lithium nitride, according to this equation. Magnesium and nitrogen can react in a similar manner to form magnesium nitride, according to this equation. This is actually one that you would have done in the laboratory. And if you look at where lithium and magnesium are on the table, right, they are diagonally next to each other. So there's lithium, magnesium is underneath and to the right. Similarly, beryllium is over here, and aluminum is down and to the right. And then boron is here, and silicon is down and to the right of it as well. Right? So that's a diagonal relationship we see in a few places. That's another general trend in reactivity. So this brings us then to hydrogen, which is the first element in the periodic table, electron configuration 1s1. And where we find hydrogen on the table, obviously, is in group 1 because it's got one valence electron, just like the other elements in group 1. But really, hydrogen really does belong in a group on its own or by itself. So it technically belongs by itself because, yes, it's got one valence electron. Okay, this one electron here. And it can lose that one electron to form H plus, just like the other elements in group 1 form a +1 charge. But then it can also, depending on what it's combined with, it can also gain one electron to form the H minus, the hydride ion, which behaves very differently than the H plus ion, obviously. But we put it where it is because that's the most applicable place for it, and it's got that one valence electron, which is similar to the other elements in group 1, right? So hydrogen can form a cation with a +1 charge if it loses one valence electron. It can also form an anion with a 1- charge, the hydride ion, depending on what it is that it is combining with. So it's sort of versatile in that sense. It's also very unusual, and again, really, it technically belongs in a box or in a group on its own, rather than in the group 1. Okay, so when it forms a +1 charge, it's similar to the group 1 elements. When it forms a -1 charge, it's actually more similar to the group 7 elements, fluorine, chlorine, bromine, and iodine, because they form a -1 charge. An important characteristic of our hydrides, for example, is that they can react with water to form hydrogen gas, and then we also get a base, which in this case is the calcium hydroxide in this example. All right, so we have calcium hydride here. So this is made up of the Ca2+, and then we also have 2 hydride ions. Right, that these come together to make the ionic compound. These can react with water. This forms calcium hydroxide, which is the base. We'll talk about acids and bases in the next section. And then we also get hydrogen gas as one of the products. Probably, though, the most important chemical, the most important compound, the most important substance that has hydrogen in it is the one that we all cannot do without. right? And that would be dihydrogen monoxide, commonly known as water. All right, so let's take a look now at the first group, the group 1 elements. All right, remember these are the alkali metals. These generally have low ionization energy, so they easily form our metal, let's say M metal with a charge of 1 plus, right? They have that one valence electron that they can give up very easily, and as a result, they're never found on their own in nature, right? They're actually found in combination with other things because they're so reactive. So found naturally in combination with other things. Okay, so for example, if you take a look at some of the group 1 metals, they in some cases can react violently with something as simple as water. So for example, they can react with H2O. So if I have my generic metal M, can write an equation. Our metal M here, the group 1 metal can react with H2O. We end up forming the hydroxide, so the metal hydroxide, and then we also get hydrogen gas as one of the other products. This obviously is unbalanced. You need to balance that equation. But that's a general way in which those actually react, the alkali metals with water to form the hydroxide and hydrogen gas. All right, so they're super reactive. Now, that's reaction with water. If they are exposed to the air, they can also react, in some cases, vigorously. So, for example, when they are exposed to the air, they eventually lose their shiny coat because they react very quickly with the air. They form a coating on them, and they become less shiny over time. They form the metal oxides. So, for instance, lithium forms lithium oxide. So it reacts with oxygen to form lithium oxide, which is Li2O. And again, these are unbalanced reactions. You need to balance these. So we found the oxide of lithium. Other alkali metals can either form oxides or peroxides. And peroxides is another form in which oxygen can react to form or to begin a compound. So for instance, sodium can react with oxygen. We end up forming Na2, O2, or the O2 here, that's the peroxide ion, right? It actually has a charge of -2. So the peroxide ion here that's another polyatomic ion, a new one that we haven't seen before. And some of the other elements, so even others can form other sort of exotic classes of oxides known as superoxides. Okay, so for example, something like potassium can react with oxygen to form KO2. Right, and the superoxide ion has a charge, or it's O2 with a minus charge overall on it. So the type of oxide then that an alkali metal reacts with oxygen has to do with the stability of those different oxides. Some are more stable than others, and those are the ones that would be preferred. So lithium, for example, tends to form predominantly the oxide, regular lithium oxide, because lithium oxide is way more stable than lithium peroxide, for instance, right? So it has to do with stability, which again is a driving force for lots of things in chemistry. So those are the general reactivity of the group 1 metals. If we look at the group 2 metals, we're going to see some similarities, also some slight differences. So the group 2A metals, these are the alkaline earth metals. Okay, and for example here, what we will see is that these generally form the metal with a 2+ charge on it because it'll lose those 2 valence electrons. The reaction with water can vary tremendously. So they can vary a lot. For example, so beryllium, for instance, does not react with water, but magnesium can react slowly with steam. And then calcium, and barium, and strontium, they can react vigorously even with cold water. So when they do react, so for example, if you have something like, let's do barium. So barium can react with H2O. And again, we're going to get something similar as with the group 1 metals. We're also going to form the hydroxides. So we end up with barium hydroxide, BaOH2. Then we also liberate hydrogen as one of the products. This again is unbalanced, right? So this would be a vigorous, very vigorous reaction. The higher up in the group you go, the less vigorous it is. So something like magnesium will react only slowly with steam. So the reactivity then of the alkaline earth metals increases as you go down the group towards water. The reactivity also increases towards the reaction with oxygen. Right, so beryllium and magnesium form oxides only at super high temperatures, but calcium, strontium, and barium can form the oxides at relatively low temperatures, right? So if you use barium reacting with oxygen, we end up forming the oxide BaO. And that again is an unbalanced reaction. The last sort of comparison here is the reaction with acids in this case. Magnesium, for instance, can react with aqueous acids to produce hydrogen gas. Calcium, strontium, and barium can also react with aqueous acids to produce hydrogen gas as well. So for instance, we have Mg, magnesium, reacting with an acid. We'll represent an acid with an H+, because that's what acids produce. We end up forming Mg with a 2+ charge, and then we liberate hydrogen gas as one of the products.